All right, so this is video 2 of the special relativity section of this. So we have already talked about time dilation, which was the really weird thing that happened with time depending on how you were moving. So we had that t moving is equal to t rest over the square root of the weird 1 minus v squared over c squared. All right. So I talked a little bit about in class today that there's actually a problem that comes up with using this formula because of the whole not being able to get to the place. So let's actually look at that real quick. So if we are, let's say, in a spaceship, and our spaceship is going to the nearby star Alpha Centauri, and Alpha Centauri is a total distance of 4 light years away. Okay, so it's a relatively uh, near star, 4 light years away, and we are going to be traveling at a velocity of, again, about 80% the speed of light, so 0.8 c. So we figured out that today in class that we could say, okay, if we're going 4 light years, and I'm going to write it in a special way, 4 light years using c for light, and I'm going about 0.8% the speed of light, or excuse me, 80% the speed of light, then c's will cancel out, and we get that the whole trip, according to the reference frame on Earth, should take about 5 years. Okay, but we know that the people on the spaceship won't experience the entire 5 years. This is what it's going to be on Earth. It's going to take 5 years for us to see that spaceship get there. So on the spaceship, we know we can use the time dilation formula and see how much fewer years, if that's even the right way of saying that, how much different it's going to be for the people on the spaceship. So we know that t moving is going to, in this case, equal 5 years. And we know that equals t at rest over the square root of 1 minus v squared over c squared. And remember that v squared is going to equal 0.8c, that whole thing squared. And just like in class, this equals 0.64c squared, and we can use that in our new formula. So next step, we're going to take the radical and put it over here. So we get 5 times the square root of 1 minus, in this case, I'm going to input v squared of being 0.64c squared over c squared. This equals t at rest. Okay, so let's extend the page a little bit. All right. Remember that you can always pause or rewind, rewatch, anything. So we can see that the c squareds cancel out. And we're left with 5 times the square root of 1 minus 0.64. That equals TR. Okay, continue on. We would have 5 times the square root of 0.36 equals TR. And if you put that in your calculator, you get that TR is, actually, let me do it real quick, make sure that I give you the right answer. Okay, and you get 3. So you get that on the spaceship, they are going to experience 3 years. Okay, so on the Earth, it looks like it's going to take 5 years to get there. People on the spaceship only take 3 years. Okay, now here is where it kind of breaks down, because if we are actually traveling at 80% the speed of light, and it only takes 3 years for the people on the spaceship's reference frame, let's figure that out. So we would have, let's see, if we did distance is equal to velocity times time, and in this case 0.8c is the velocity, and we're going to multiply it by 3 years. This comes out to be 2.4 light years. CYRS, light years. But the problem is that if we're only traveling for 3 years, then we're not going to get to the star because the star is 4 light years away. Okay, so that means that one reference frame shows the spaceship getting there, the reference frame of the Earth. That shows the spaceship actually getting there. The other reference frame shows that the spaceship will only be 2.4 light years into the journey of a 4 light year trip. So that means there has to be some kind of change in the length, the distance between 2 points when you are going that fast. And it turns out that there is a new equation for that. And that equation is that the new length is equal to the old length times the same factor of 1 minus v squared over c squared. Okay, so 1 minus v squared over c squared, it pops up again, the square root of it. So let's check this in terms of our new problem here. So if the original length was 4 light years away, and we're going to do 1 square root of 1 minus, again, 0.8c, that whole thing squared over c squared, which, carrying this on, gives us 4 light years of the times the square root of 1 minus 0.64, which again gives us 4 light years times the square root of 0.36. And if you stick all of that into the calculator, you get 4 times the square root of 0.36, and you get 2.4 light years. Okay, which does indeed match with how far the people in the spaceship would have traveled during the 3 years that they are seeing it. So that actually means that the distance between us and Alpha Centauri, according to the spaceship, is actually 2.4 light years. 2.4 light years instead of the actual 4. People on the Earth see 4, they see the trip taking 5 years. So people on the spaceship, the trip only takes 3 years, and they've only traveled 2.4 light years. So this is a really weird concept again, where we have lengths changing because of the fact that you're traveling. So not only does movement through space affect how you move through time, but movement through space affects how you move through space. Space actually condenses, it contracts when you start to move that fast. Okay, I'll see you next time.